All right, we are at section 4.5, tangential and radial acceleration. This is going to be a short video with some examples. You can imagine a little track here. We're looking at a side view of a track, or you can think of a roller coaster. You have a dip in the track, and it goes up and then it goes down. And you can see that portions of this track are represented by circles. At point A, you have a small tight circle. At B, you have kind of a larger circle. And at C, it's so large, they don't even show you the whole circle. It's just a portion of it. But you can see it's a very, very large circle. Now, we've been studying acceleration, linear acceleration. When you're going in a straight line, if the acceleration and the velocity are in the same direction, you're speeding up. If velocity and acceleration in the opposite direction, then the velocity is slowing down. We've talked about centripetal acceleration, where things are going in a circle. You can think of a rock. You've got a rock or a tennis ball or something at the end of a string, and you're just swinging it around. The tension in the string is holding the ball in place. That's the centripetal force that's causing it to move in a circle. You can think of the satellite in orbit around the Earth. The gravitational pull is keeping it in orbit. That's the centripetal force, gravitational centripetal force on the satellite. You can think of the moon. The moon's not exactly, or you can think of the Earth and the sun. They're not. We'll learn later that they're not circular orbits. They're elliptical orbits, but we'll get to that when we study Kepler's laws. But let's just think about this. So we've only been talking about acceleration, either linear acceleration or centripetal acceleration, but now we're going to combine the two. And you can see that if you imagine this, a roller coaster car, as it's coming down this hill, it's right at the point A. It does have a tangential acceleration, which is the delta v, which is v delta t. At that point, delta v delta t. And you have a centripetal acceleration going up. Well, the total acceleration is the sum of the two. And that's true of every point. At A. At B, you can see that the tangential acceleration is backward. Here at A, it's forward. If we imagine the particle moving from left to right, at A, it's speeding up. At B, it's slowing down, because you can see the tangential acceleration is opposite the direction of the particle's path. And at C, it's speeding up once again. Gravitational acceleration is making it speed up. But at each one of these, the tangential acceleration is inward. I think I said that wrong. The centripetal acceleration is inward. Or the radial acceleration, as they have put here, AR. The radial acceleration is inward. It is the centripetal acceleration, but the total acceleration is the sum of those two vectors at every point, at point A, B, and C. So the total acceleration, A, is equal to the A radial plus the A tangential, the radial acceleration plus the tangential acceleration. The radial acceleration is the centripetal acceleration. The tangential acceleration is the absolute value of dv dt. Remember, the velocity acceleration is the time rate of change of velocity. It's also the second derivative of position. And we know that the A radial is equal to minus the A centripetal, and that's equal to minus v squared r. Let's see, I forget why it's, I should look that up, why it's minus. Let's see. Negative sign in the last equation indicates that the direction of the centripetal acceleration toward the center of the circle, representing the radius of the circle. So that's it. The direction, the unit vector r is from the origin of the circle outward. So the radial acceleration is actually pointing in the opposite direction of the unit vector r, and that's why it's negative. So the radial acceleration is negative of the centripetal acceleration, which is minus v squared r. All right. Let's. Okay, and the magnitude of the total acceleration is the square root of the radial acceleration squared plus the tangential acceleration squared. I think that's no. Let's talk about the radius. If the radius is small, if this radius is small, the acceleration is very great. The tangential or the radial acceleration is great because it takes a lot to get that to move in a tight circle. Look at point C, where the circle is very broad. The radial acceleration is much smaller. It's much smaller than it is at A or B because it doesn't take it as much because you're not changing as much on that large circle. And I think that's all I needed to say about that. Let's get on to the quiz. A particle moves along a path and its speed increases with time. In which of the following cases are its acceleration and velocity vectors parallel? A particle moves along a path and its speed increases with time. In which of the following cases are its acceleration and velocity vectors parallel? Well, if we're talking about the total acceleration, the only time that if the speed is increasing, the only time that the acceleration and velocity vectors will be parallel is when they're in a straight line. If it's circular, the total acceleration has a radial component that is going to make it. Let's look here. You see the radial component of the acceleration is nowhere near the tangential component, which is the tangential component represents the direction, the speed, the velocity vector at that moment is going the instantaneous velocity. So it doesn't count for a circular path. It doesn't count for a parabolic path. It only counts for a straight path. Okay, so that's the answer to that quiz. Now, part 2. A particle moves along a path and its speed increases with time. In which case are its acceleration and velocity vectors perpendicular everywhere along the path? Its acceleration and velocity vectors perpendicular. Well, in a circular path, the centripetal acceleration and the velocity vectors are perpendicular, but not the total acceleration. If it's straight, they're not perpendicular, they're in line with one another. And when it's a parabola, well, at the top, the top of a parabola, the horizontal velocity is perpendicular to the gravitational acceleration. But the question is, a particle moves along a path and its speed is increasing. The speed is increasing. When we looked at a parabola, only the horizontal component was constant. It wasn't increasing. So in this case, it's never the acceleration and the velocity vectors are never they're never perpendicular. And that ends this section. There's the never. The relative velocity and relative acceleration, we're not going to cover that. I am going to. I want you to watch a video on relative it's actually called frames of reference, and it really covers what these it covers these better than what the this description covers. So we'll end it here.